Alrighty, members of the aluminum kingdom, let's take a look at bend allowance. In a previous video, we identified bend parts, discuss what role they play, where they can be found. Now let's look at how to use this information, include some math, and start solving for a few things. Once again, I recommend that you stop the video, draw this out. One thing that's very important, and I always put a lot of emphasis on, if you look at this area here, I've got an order that I'm doing this thing. Now, there's no rule that says or states that you have to figure all this out in a specific order, but there is some common sense. Anytime we're going to go to calculate layouts for bends, there's always going to be some givens. They're going to be given to us either by the engineers through the use of drawings. They'll be given to us by being able to measure an old part in order to make a new part to replace it. But some givens will always be there, and thank goodness for that. We got to calculate a few things here, and let's start. Now, it may take a few of these short videos to get this, but we're going to have to determine it. I'm going to add one thing to this list that we're going to focus on to start with, and that's bend allowance. If you remember from a previous video, bend allowance is the amount of material that we're going to need to set aside. We need to set that aside in order to form the bend. In a flat layout, it's represented right here. We've got a flat A, we've got a flat B. We'll call this one B. We'll call this one A. So we need to determine how much flat metal is needed to make this piece, but we also need to determine how much material is going to be needed to make this curvature or radius of this bend. So let's start solving for some things. In this case, our given is our metal is 40 thousandths of an inch, and the radius that they want us to form is 0.1875 or 3/16 of an inch. They want the width. This is like making a clip that we're going to rivet on something. The width is specified is 2.0 inches, so that's a given. Well, one of the first things we want to do, and as you can see it on my list here, is let's solve for setback. And remember, what setback is simply the material thickness plus this radius. So if we started at this mold line, measured over to this bend tangent line, that's our setback. Now the setback is done for just that reason. It gives us that bend tangent line. Where should my bend start? Where should it stop? Setback establishes that line on our flat layout. Well, how do we arrive at that? Well, we simply, setback is always equal to metal thickness plus radius. So if we take 40 thousandths and 0.1875 or 3/16 of an inch, and we add that, our setback, simple calculation, 0.2275 of an inch. Well, now that helps me because I know now the distance from there to there. That's going to help me establish where I can put my first mark. But right now, the overall length is incorporated into this leg. Well, we don't want a leg. A leg is from the very end to the mold line. I want just the flat. So I don't even have to know the math. I can see if I subtract my setback measurement from my leg, that will give me my flat. So flat A, we'll come down here and calculate. Flat A equals the leg length of 1 inch That'd be 1.0 minus what? That's right, our setback, 0.2275. Now, if I subtract 0.2275 from 1 inch, I should end up with 0.7725 of an inch. So I could come down here and identify, in this case, since they're the same, if we've done the math for one, we've done for both, because both have 1 inch legs. So I would simply do that math, leg minus setback, and I would measure in 0.7725, and I'd create my first bend tangent line. That establishes my distance. However, I need to allow for metal to go around that radius, and we do not have a handy solution for that. Well, I will cover the longhand math way of arriving at that, but I'm also going to show you a common option. And it may take me a moment to zoom in here, but we're dealing with 40 thousandths material, so I could go to my column, my left-hand column gives me my metal thicknesses, and these rows across the top give me my diameters. So I'd simply go to 40 thousandths, come over until I intersect with my diameter, 3/16 of an inch, and look at there. It's already been calculated for us, 0.323. So with that new information in hand, let's go over and write that in to fill in our blank. And then we will know what our measurements is right here for our bend allowance, 0.323 inches. Now we said earlier, since both legs from the end of the metal to the mold line are measured at 1 inch, we solve for a flat by saying leg minus our setback. Well, we come out to flat A is 0.7725, and flat B would be 0.7725. Now, it was kind of simple for this little clip to calculate this, but if your leg lengths were different, let's say flat A was a 2 inch, we'd simply substitute 2 for 1. The setback would remain the same, and we'd have ended up with 1.7725. So I'm going to come up here and write in, as I solve for these, flat A is 0.7725 inches long. Flat B, since it's the same leg length, it'll be the same flat length. Our width is 2 inches. Our bend allowance is 0.323. The only thing we don't have here was our degree of bend. And typically that's given to us as well, especially if we're manufacturing a new part or modification. Well, in this case, we were on a 90-degree bend. That's important to know as well, because when you calculate setback, that distance from here to here, we'll just write that in as a setback right there. When we use these charts, degree of bend is important. Let's go back to our 40 thousandths and 3/16. Our bend allowance, or metal we needed to set aside to go around the turn, for a 90-degree bend was 0.323. Right beneath that in all bend allowance charts will be another factor. This factor, 0.003593, would be how much metal we need to allow per degree. That's very important. So if we were bending something other than a 90, let's say if we were bending a 45 degree, we would need to use that factor multiplied times 45 to figure out how much metal to allow to go around that bend. That's also an FAA question. What two factors are found in bend allowance charts? Well, the first is your bend allowance for 90 degrees. The second factor, typically below the first, is your allowance per 1 degree of bend. But right now, since we're focusing on a 90-degree bend, it was pretty straightforward. Now there's one thing left to solve. We have looked at our metal thickness plus radius to give us our setback. We got our setback. Leg minus setback equals the flats. We solved for that. 2 inches was the width. That was a given. And we went to our bend allowance chart for this 90-degree bend and determined we need 323 thousandths of an inch of metal to allow for that radius to form. Now we've got one other thing we need to put in. And I'm going to draw, and this will be kind of loose and probably not so pretty, but I think it'll be a little bit cleaner. If we were to go back and label this, remember this is a flat, this is our bend allowance, this is a flat. We've got those dimensions. We always must put a line in that we're going to use to bend by. This line's very important. We haven't discussed it in previous videos. This line is referred to, and let me find us a little area out here where we can, this is what we call a sight line. Now, a sight line is always going to be equal to 1 radius. So if we go back up to our list, we find our radius. We would simply measure over from this flat 1 radius, which is 0.1875. We would draw a line. It won't always be in the middle. What this is when we put this piece of metal in the sheet metal brake, it's going to go in like this. That is the line, if we look straight down the edge of that sheet metal brake, that we'll line up with. See, there's a problem with bending metal with radiuses because everything we're bending is based on that shape. Where my metal should start bending for a 90 degree and where it should end up bending for a 90 degree is actually clamped under where we can't see where the mark would be. So what a sight line does, it puts a line that we can look straight down that edge, line up on and clamp, and that'll allow us to know that our metal's going to start bending at the right location, and if it does, it'll stop bending at the right location. So this is how you can do the math to determine how to make a bend. Now we've got to cut our piece of metal. So what we've ended up with here by doing all this math is we've got all the information we need. It needs to be 2 inches in width. And now, if we take flat A plus flat B plus our setback, we could easily do the math to calculate for the length of our layout. Well, I'll take flat A, 0.7725, plus flat B, 0.7725. Then I'm going to add, that's flat A, flat B, we're going to add that bend allowance, 0.323. And by golly, we've got our total length of our layout, which is 1.868 inches. So to make this project, we would cut a piece of metal out to that length. And if you say, Jay, you told us to get this ruler, and there's none of those small decimals on it, and I got to looking, and hardly any of this stuff works out neatly into a fraction. Here's a simple solution. We'll take a pair of calipers and we'll use the calipers to lay out and make our precision measurement. Then we can mark exactly where all of these lines need to be to cut the piece and to form the piece to create this bend. Now I'm going to do some more videos on this series, but I would like for you to practice this. Once again, our givens, typically our metal thickness, the radius required, the width, and then we can solve for the rest of these using our procedure. Follow that procedure and you'll find that you have a high degree of accuracy. Now, using the bend allowance chart, absolutely, that made life much faster, much simpler. All these calculations have been done. I have no problem at all if one of my students utilizes a chart, but I will do another video to show you how to find bend allowance in case you run into something that you don't see on the chart, or in the case that, well, you just didn't have a chart with you. But these days it's very easy to look that up on your cell phone, and you would have that chart handy at all times. As a matter of fact, I downloaded one and just saved it, so I have one. But this is how you use your bend allowance chart. This is how we walk through solving what our flat layout dimensions are supposed to be and our marks on that layout in order to produce a by-the-book bend using the exact right amount of material. At this point, there's one thing left I want to discuss. If I have a radius that's, let's call that our 3/16. Well, say I have a smaller one. It's a little tighter. Let's say that is 2/16 or 1/8. I want to point this out. This piece of material, total layout, will be shorter than this piece. And I know that seems backwards, but here's the fact of the matter. It takes more material to go to a corner, stop, and take off if the corner is small. I kind of equate it to cutting across the old man's yard in the neighborhood. I've always told my students that the more you cut across a corner, the fewer steps it takes. So in this case, 1/8 is a smaller radius. I've got to walk almost completely to the corner before I change directions. 3/16 is a larger radius. Therefore, I'm going to cut across the corner of the old man's yard. I'm walking down here, I cut across his yard. Larger radius means I cut further through his yard, which means I make fewer steps and I need less metal. There's some questions on the FA exams that'll ask, simply put, given two radiuses, which one would use the least amount of metal or the most? Remember this, the larger the radius, the less metal you'll need to make the part. Thank you for watching the video. Stop and start and practice. Come prepared with questions, and as always, do good work and be safe.